Okay, so in the last few videos that I've made, I've kind of worked through several examples of how to write functions as power series using those algebraic tricks, writing them as the sums of geometric series, and examples of how to write different functions as Taylor polynomials using this little formula right here. And in the last video, we had actually used it to approximate the value of a function, I think ln of x, at a given point around the interval of convergence. And we kind of left with the thought, well, this one right here, this is another one, sine of x, standard, we've done it before, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And we can use that polynomial to approximate the value of sine of x on the interval of convergence. And we can worry about the interval of convergence later on. For right now, since this is a Maclaurin around 0, we could say maybe use it to approximate f of 0.2. And we understand how to do that. I plug 0.2 in here, here, and here, hit enter on my calculator, write out all the arithmetic, whatever you want to do. And the value I get would approximate the sine of 0.2 right there. Because again, a few hundred years ago, they couldn't do that by hand. They could do it by hand. They couldn't do it on a calculator or a computer. So this trick is what they use to approximate that. But then kind of the natural follow-up question is, whatever value I get here, is it good enough? Is it within the error that I want? And we haven't fully developed the idea of the error yet, but we understand the principle. If this was not a good enough approximation, what would I do? I'd throw the next term on there. And we can tell here by the pattern, the next term is clearly going to be negative x to the 7th over 7 factorial. I can plug 0.2 in there, figure out the new value, be good to go. And then if that was still not within the error that I wanted, go to the next term, which would be x to the 9th over 9 factorial. And hopefully that would be enough terms, because that's going to take a while to write out. But essentially, we understand the principle. This is a polynomial. It approximates the value there. And I simply go far enough along the polynomial to get within whatever error it is that I'm looking for. But there is actually another trick here, and one of the things that Taylor was kind of pointing out with this is a polynomial which stops. It's 9th degree polynomial. I can stop at any n I want. But this series right here is actually infinite. It goes off forever. And what Taylor says is, this is a polynomial which stops, which is why it's an approximation of the function. But if I let my series go off forever, so I guess the next term will be negative, so I'll just do negative, dot, dot, dot. Now, this is the infinite series that represents that. And Taylor says these are actually equal. Sine of x is equal to that series right there. The problem is, in the real world, I can't actually evaluate this infinite series because it's infinite. I can't plug in a value for an infinite number of terms. So in the real world, we stop at the 5th degree, the 7th degree, the 9th degree, whatever. We figure out how much error we want, and we use that to approximate the value of the function. But Taylor says, if I actually looked at the infinite series and could evaluate it, the infinite series would be the function right there. In one of the other videos that I did when we first defined these Taylor things, we found the Taylor polynomial for sine and the one for cosine, and we saw that if we took the derivative of the one for sine, we get the series for cosine, which makes sense because this series represents sine. The other series, cos of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc., etc., etc. That series represents cosine. So the derivative of this series has to be that series because they're derivatives of each other. Sine goes to cosine. And essentially then, what that means is we're kind of stuck in this limbo where mathematically I can say the function sine of x is equal to an infinite series, but I understand that I can never evaluate that infinite series because I can never evaluate something that's infinitely long. I have to stop at some point. So I create these approximating polynomials, because I can't evaluate the series. And the question we get left with is how much error is involved when I truncate my polynomial, when I take my series and I stop at some point along the polynomial. And here is where I'm going to copy this right out of your book to make sure that I actually use the same terminology as your book. And essentially, we have a function f of x is equal to this series. We'll say n equals 0 to, your book uses, well, it goes to n. So we'll say n to infinity, f to the n of a, x minus a to the n over n factorial. So we take a function, for the sake of argument, we're not going to solve it again because we just did it, say sine of x. And I want to find a way to represent sine of x as this series, which we have done, which is infinite. But then I want to know how much error is going to be involved when I truncate my polynomial. And so I end up with this remainder term where essentially sine of x, or f of x, ends up equaling a series from, say, 0, we'll say, to k, of f of n of a, x minus a to the n over n factorial. So essentially I take the kth polynomial plus I have some remainder term. And your book uses which letter for their remainder, which subscript? N. R sub n of x right here. So I can either say the function is the infinite series, or I can say this is a polynomial, it's a kth degree polynomial, plus there's the rest of the series part that I'm not actually using. That's my remainder right there. And you could argue, or at least if you think about it, because we've kind of done this before, the question is, what is that remainder, and can I figure out what it is? And the answer is actually no. And there's kind of a principle here. If you think about it, I can write a function as a series which is infinite, and I can evaluate it. Well, no, I can't evaluate it because it's infinite. But I can at least write out the series, the general series, but I understand that I can never actually evaluate it because it's infinite. But here, I can definitely evaluate the polynomial right here, because that's a polynomial. I stop it at some kth degree, and then I can evaluate that and get a number. So I get a number here. If I got a number here for the remainder, well then this series would equal this number plus the remainder, which is another number, which would mean I actually evaluated that series, which I just said I couldn't do. That's actually why I did this down here. So again, there's a subtlety here and a kind of an important note where this is the general way we write things, and it is completely mathematically true. I can write sine of x as an infinite series, the one I had written right up here. And that is the series representation of sine of x. But if I actually want to use it in the real world, I have to evaluate it with a polynomial. And I understand that if I evaluate it with this polynomial, there will be a remainder, an error involved, and I can never actually know what that error is exactly. Because if I knew what the error was, then I would actually know the actual value here, which I can't know. Because if I could know it, then I could solve this, which I can't. And I'm aware that's a slightly bizarre way of looking at it, but that's the way it works. And to actually get, I'm going to erase this now, to actually get this error, we have this right here. And I've said this before in class, and I will say it again. I don't necessarily like the way your book writes things in the lettering, which is why I'm looking at your book, because I like to write this differently, but I want to keep it in agreement with your book. So the remainder is less than or equal to m all over n plus 1 factorial. And actually, because I want to make it agree with this, since we went to the kth degree here, that's k plus 1 factorial times the absolute value of x minus a to the k plus 1. And for this m right here, it has to be true that m is less than or equal to, actually, no, it's greater than or equal to, I wrote it backwards, f to the n plus 1 of x, absolute value is less than or equal to m for all x's in your interval of convergence. And again, that's kind of a long, involved way to write it out, but all things being equal, this is pretty straightforward right here. For the sake of argument, suppose I had a 5th degree Taylor polynomial with a equal to 0 for a function. Well then, right here, the degree is my k, so my remainder would be less than. This would just be 5 plus 1 factorial, which is 6 factorial. This would be x minus the center, which is 0, so that's just x, to the 6. M, to get m, you take the k plus first derivative. I wrote n because I used n here, but take the n plus first derivative, which for us would be the k plus first derivative. N has to be greater than or equal to every value of that derivative on the given interval. That is actually similar to what we had for Simpson's rule and the trapezoidal rule, so that should make sense to get my m right here. Again then, the only actual real problem is finding this right here. Because if I want a numerical value here, well, I need to find an x. And again, if I could find an x to actually make this work, well then I'd be able to solve this out really nicely. And well, then I'd be able to figure out my remainder really nice and good, which we've already established I kind of sort of can't. How to actually work one of these out takes a few minutes, and I want to work through one. So for right now, we have the formula. I'm going to make yet another video where I actually work through one of these and show you how to find the error, or at least approximate the error, using all of these formulas right here.